Okay, thank you for logging in. And I'm still recovering from COVID, so I can't be with you. So I prepared this video to actually introduce the last chapter of the syllabus to you. It is called EMI, Electromagnetic Induction. So before I begin the chapter, let's start with a question. So have you ever wondered when scientists actually is developing electricity, let's say they are studying electricity, how do they actually study it before? Because voltmeter and ammeter are actually invented after they discover that they can use charges to transfer energy when they were first when they first discover that there's this thing called charges in a wire, and they can use electrostatic forces to move the charges in one direction. So what do they use to measure the current that they produced before they invented the ammeter and voltmeter? So to your surprise, they actually use frogs. So it is pretty interesting, and let's watch this YouTube video.
How do you measure electricity before you've invented the voltammeter? How about with a frog? This was Michael Faraday's solution to testing electrical circuits back in the 1820s, before more sophisticated methods had hopped along. Down in the basement of the Royal Institution, Faraday and his mentor, Humphrey Davy, kept a well-stocked froggery, jumping with healthy frogs. On the occasion that electrical equipment or circuits needed testing, they would select a willing participant, hold it by the legs, and smash its head in to render it, well, dead.
We are joined together today to celebrate and...
So if you recall, I usually will ask this question: how do you move your fingers? So the way our brain communicate to our muscles is by the nerves, right? So our brain will send an electrical signal through our nerve system, and then our muscle will either relax or tense up, and that creates the movement that we want. So similarly, when Faraday is conducting experiment, he would actually wire up the circuit to a frog leg, and if they pass a current through the circuit, the frog leg will actually twitch in response to the current. So something like this. So as you can see, the legs are moving on its own when a current passes through it. So obviously this is a very cruel and crude way of measuring current, but that is what Faraday did. And legend says that some story in some science books mention that when Faraday is conducting this experiment of wiring up the frog's leg to his circuit, one day he made another discovery. So when Faraday hooked up the frog's leg, he actually forget to 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 include the battery or the source of the electricity in his circuit. But yet after he realized that he didn't put in any power source, miraculously he also found that the frog leg is twitching. And it is a big deal to him because for at that time, the frog leg twitching is a concrete proof that there is this thing called current flowing through a circuit. So when he discovered that without a power source, the frog leg will actually twitch with just a closed circuit, it means two things. Either there's something that can replace the missing power source, or number two, that he has created a false method of proof to show that there's current in the wire. So Faraday got very worried and anxious because it's either he had a new discovery, or that he has come up with a proof that actually doesn't confirm that there's current flowing through in the circuit. So to him it's a kind of like a win or die situation. Then later on, when he carried out more experiment, he tried to repeat this to see what are the conditions that actually cause the frog leg twitching. He realized that the frog leg will only twitch without a power source only if his colleague working next to him comes to work. So then it got him very puzzled, and in the end he actually found out that his colleague is actually studying magnetism, and when he comes to work, he will actually move the magnet on his laboratory bench very close to Faraday's bench. So he realized that, uh, when the colleague move the magnet, then the frog leg will twitch. And if he left the lab, the magnet is still there. So when his colleague leave the lab, then no one will move the magnet, right? And he find that the frog leg will not twitch. So later on, he carry out more experiment, and he find out that he make a new discovery. So this new discovery basically sets the foundation of this topic, EMI. So how does this work? So previously in our chapter, we found that when you have a magnetic field from a permanent magnet, and if you apply a current in the wire, it will generate another magnetic field, and these two magnetic fields can interact, and eventually you will have an induced force on the wire that causes movements. So in this chapter, what Faraday has discovered is that if you have a magnetic field around you, and if you apply a force either to the magnet or to the wire, so as long as there is relative movement between these two, so relative movement means that you can either move the magnet or you can either move the wire. When there's relative movement, Faraday discovered that actually you can induce a current in the wire. So it is a rather huge discovery because it enables you to turn kinetic energy or work done by that particular force into electrical energy. That means you can transfer the energy from one place to another by electrical means. So it is a great discovery, and basically Faraday come up with this law as he studied the patterns and all that. And this law is called Faraday's law. Basically it tells you that you can actually induce an EMF, and this the amount of this induced EMF is directly proportional is directly proportional to the rate of change of magnetic flux. So this rate of change of magnetic flux is actually a mathematical idea that is not in your syllabus because it is actually a differential equation. So for those of you who wanted to know what is rate of change of magnetic flux, flux actually has the symbol that looks like this. And rate of change of magnetic flux, basically you have to differentiate this with dt. And unfortunately this flux is actually a function, and this function is your magnetic field line cutting through an enclosed area at an angle. So if it is cutting through the area at 90 degree, cosine 90 will give you 1. So the cosine 90 term can become 1 and dt, and then you need to break it down into your chain rule. I hope this is called chain rule because I kind of forget what it is called. Or it's called product rule. I forgot already. Yeah, so but this entire mathematical term, right, you are not required to know how to manipulate it at O level, so you can forget about this. But sometimes when you are asked to define or state Faraday's law, you need to be very mindful that Faraday's law says that it is induced EMF. Pay attention, it is not current. Okay, and when you want to state the Faraday's law, you have to remember that it is magnetic flux that is involved. It is not field. Okay, so you have to use the exact word. So unfortunately for this particular part of the topic, you need to really memorize what's the word that is being used. So after Faraday's discover this phenomenon, he called it he named it Faraday's law, and we can reproduce this experiment, and we can measure the quantity to confirm that Faraday's law is correct. So let's watch this video. So in this video, I just want you to pay attention to the ammeter. As you can see, it is a very low current, right? It's microampere. And I want you to also observe that only when there's relative movement between the magnet and the solenoid, then there will be induced current. And you can see that the induced current can either go in the clockwise direction or the anti-clockwise direction, depending on how the magnet is being moved relative to the solenoid. So do you see, when the magnet is being pulled away, the pointer actually goes to the right, and when the magnet is being pushed into the solenoid, the pointer moves to the left. So let's repeat. Oh, excuse me. So just now she flipped the pole, and that's why the whole dynamic reverse. And you can see when the magnet is stationary relative to the solenoid, there's no induced current. So we can actually reproduce Faraday's experiment and confirm that his law is actually working, right? But since you have not been introduced to the differential equation that is involved, for this chapter there's no mathematical calculations. It's purely on how you explain. Yeah. So let's try one question and see how can we apply Faraday's law to explain the phenomenon whereby when you move the magnet relative to the solenoid, you can actually cause a change in the ammeter. So for example, this question, it says that you have a solenoid connected to an ammeter, that's an iron core, and then you have a magnet. Basically this arrow here is showing you that this magnet was being pulled away from the solenoid. And you can see that whenever you are doing questions on EMI, you will see that there is actually no power source, right? Because when you are dealing with electromagnetic induction, you are trying to induce the EMF, so therefore you will not have any power source. And because in this question you are asked to explain why is there a reaction to the ammeter, you need to end your explanation with how a current is being induced. But you realize that for your Faraday's law, it actually talks about induced EMF. So at the end, you will need to, although I know it is quite troublesome, you need to mention that since there's an induced EMF, hence there's an induced current, and therefore there's a reaction in your ammeter. So let's go through how do we give a very complete answer. So when you answer such question, you need to let the examiner know that you are aware of the trigger condition, and that is there must be relative motion between the magnet and the solenoid. So in this case, that particular relative motion is that when the magnet is being pulled away to the right, you will then have a relative motion, right? So once you have a relative motion, you need to be able to highlight what is this rate of change of magnetic flux. But because you are not equipped with the mathematical knowledge of what a magnetic flux is, you need to follow a very strict way of phrasing this particular phenomenon. So the way to phrase it is that you need to identify that particular conductor that is experiencing this rate of change of magnetic flux. So in this particular context, the conductor that is having the induced current must be the conductor that experience this rate of change of magnetic flux. So this conductor would be your solenoid, not your iron core, because your induced current is going to be induced. Your current is going to be induced on the wires, not the core. So here, you will need to mention that it is the solenoid that will experience what kind of change that we are talking about. Is it just a change that is like a vibration changing, or is it like a decrease or increase? So since the magnet is being pulled away, we would know that the solenoid is actually experiencing a decreasing magnetic flux. Then after that, this entire part has to be copied. Okay, word for word, you need to give it to me. Okay, and the keyword here is linking to that particular magnetic source. Okay, so it is very similar to when you want to talk about moment, you need to tell me that it's moment about a particular pivot. So in this case, you need to tell me that the solenoid experience, this keyword also must be used. Either you can tell me increasing, decreasing, or changing in the case whereby there's vibration, a magnetic flux linking to the permanent magnet. So it is a fixed way of phrasing it. Then finally, quote the law. But like I said, Faraday's law actually mentioned that it is an induced EMF being produced, right? So up to you. You can either say it as an EMF will be induced. This way also can, or you can say that an induced EMF is produced. So I leave it up to you. But last year, most of my students like to phrase it as an EMF will be induced. So I leave it to you. But like I said, because you are trying to explain why there is a reaction on the ammeter, you need the final line whereby it says that this EMF that induced is the cause that there is an induced current, and because of having this induced current, why so legit one? An EMF will be induced. Okay, will be induced across the circuit, and a current flow through the ammeter, right? So at this point, basically what I have done is that I have introduced to you what is Faraday's law, right, which is basically a ratio lah. It's trying to tell you that the induced EMF is directly proportional to this new mathematical term called rate of change of magnetic flux, right? And then I also share with you how you can use Faraday's law to explain why when there is relative motion between magnet and solenoid, then there will be a measurement recorded on the ammeter. Okay, I will pause here and you can take a short break before you go to part 2 of the video.